the video where you and Matthew talked about it, but I was still kind of confused on what was happening, so yeah.
Oh, okay. So, okay, let's look at it. So I have a couple of moment generating functions, right? Whoa. Here, let me go like this. Oh, wait. Okay. So, okay, we're under the assumption that X and Y are independent. X and Y are independent, okay? And the moment generating function of X, it's like e to the, it's e to the 2t, or e to the 2 e of t, e to the t minus 2 or something. So all of that is in the power of the exponent, right? And then the moment generating function of y is equal to 3/4 e to the t plus 1/4 raised to the 10th. And they wanted to know, okay, so first of all, what's the probability that x plus y is equal to 2? Okay. Yeah. Right. Oh, yeah. Now, okay, this is all coming back to me now. There are a couple of ways you could proceed. One is to create the moment generating function of the sum, because you know that the sum of the moment generating function, or the moment generating function of the sum, what's that going to be?
The product of the two moment generating functions.
Yeah, that's right. Because after all, I mean, let's just think about this. This would be the expectation of e to the t times the quantity x plus y. And this would be, I mean, I'm just showing you why this is true. This would be the expectation of e to the tx times e to the ty. And because I have independence of x and y, this would be the expectation of e to the tx times the expectation of e to the ty, which is, of course, the moment generating function of x evaluated at t times the moment generating function of y evaluated at t, right? So one way that you could do this, and this is, I think, the one that ends up being a little bit fierce, is you could say, well, you know, the moment generating function of x plus y of t is equal to the product of these two things. 3/4 e to the t plus 1/4 raised to the 10th times, I'm going to write what they did, exponential of 2 e to the t minus 2. Okay. Now here's the thing. You could, in theory, right. You could, in theory, actually figure out like I talked to you guys about the probability generating function, didn't I? Didn't I do that before? Yeah. So the probability generating function of x plus y is, you know, p x plus y of t. What's it good? How are the probability generating function and the moment generating function related to one another? What would I have to do to get the one from the other? Do you remember? If I want to get the probability generating function from the moment generating function, what would I have to do?
Don't you plug natural log into the moment generating function?
Yeah, that's right. Okay. Because if I do that, I mean, think about what that's going to do. Okay. You know, it's going to be, so look, I mean, look at this right here. If I were to plug t equal to, if I were to replace t with logarithm of t, this would become, this would just be the expected value of what? Well, it'd be e to the logarithm of t, so it would just be t raised to the x plus y, because e to the logarithm of t is just t. You know what I'm saying? And so you know that this thing right here is going to be the probability generating function, right? So that is the probability generating function of x plus y evaluated at t. Okay, and for instance, if I were to write this thing out in full detail, you know, I would see things like, you know, some kind of constant. Well, what would this be? It would be like, you know, I might have like t to the, you know, t to the first times, what would be sitting next to t to the first power? Well, it would have to be the probability that x plus y was equal to 1. Does that make sense? Wherever t to the first was, or and I might see like t to the, you know, t to the 10th in here, and that would have to be multiplied by the probability that x plus y is equal to 10, etc. Okay? So what happens with this? If I plug in logarithm of t for t, right there, and right there, you know that e to the t, or e to the logarithm of t is just t, so this is going to be 3/4 t plus a fourth raised to the 10th times the exponential of 2t minus 2. Does that make sense? Now, that might not seem all that helpful at first. I think what I did with Matthew is we then proceeded, I mean, I think that we then proceeded to take some kind of derivative of this thing, right? I mean, because how would you get, you know that this is going to be some kind of, you know, expansion of polynomial here. So hang on. So let me see. Generating function. Yeah. So how would I get, you know, I have this function right here. You know that this is going to be like, you know, p of 0 plus p of 1 times t to the first plus p of 2 times t to the second plus etc. Right? All of the probabilities. So p of 2 is the probability that x plus y is equal to 2, for instance. How would I get, you know, what I really want here, the problem is asking to compute the probability that x plus y is equal to 2, at least the first part is, which is just, you know, little p of 2, okay? How would I get p of 2 from this? What would I do? What do you think? With this guy right here, what would I have to do? What do you think?
Take the second derivative and then divide by 2. 2
Yeah,
factorial,
take the
really.
second derivative and then like divide by 2. You understand what I'm saying? Right? So, I mean, think of, so like if I took the second derivative, that would kill off the first 2 terms, yes? And dividing by 2, because when I take the derivative, this p of 2 gets multiplied by 2, okay? So notice that p of 2 is equal to this guy differentiated twice. And then what am I going to plug in to kill everything up here? Because I want to get rid of everything up here. All of that stuff is still going to have a factor of t. Yes? So what would I have to plug into this thing?
P equal to 0.
Yeah, I would plug in 0, and I need to divide this thing by 2. Does that make sense? You would need to take the second derivative, evaluate it at 0, and divide by 2. That's how you would get this. Okay? And you could do that, right? I mean, taking the second derivative of this, taking the first derivative is a little bit annoying because you would have to use the product rule and the chain rule, correct? Taking the second derivative would be slightly more annoying. But then all you're going to do is then plug in 0 and divide by 2 to get the probability in question. Is what I'm saying making sense here with doing this? Okay. But there's also another way to proceed, and that's to actually recognize these moment generating functions. Do you recognize those moment generating functions? Do you recognize them? So like mx of t was equal to 3/4. And by the way, all this stuff that we just did, was it 3/4 plus 1/4 raised to the 10th? And sub y of t was equal to, maybe if I write it this way, exponential 2 times e to the t minus 1. Okay. So let me hey, let's you know, let me remind you of something, okay? Let me just remind you of something. Do you okay, so suppose I'm going to use a couple of other random variables. Suppose u was distributed as binomial with n trials in proportion of success p. What would be the moment generating function of u? Well, it would be the expectation of e to the t u, right? And this would be equal to the sum, you know, x going from 0 to n, because remember, binomial means n trials, and I'm counting the number of successes. What is the probability of getting x successes in n trials with proportion of success p? I'll give you a hint. It's n choose x times something, right? Remember, I have to choose where the x successes happen. But then what?
Is it p to the x times 1 minus p to the n minus x?
Yeah, I'll write q to the n minus x times, okay, that's the probability of getting x, but then I have to go e to the t x, okay? And if Paul were here, he would immediately say to do what with the p to the x and the e to the tx? What would he do with those? Well, I think that Paul would say to go like this. Yeah? Put it all under 1 power of x. Q to the n minus x. Okay? And that looks like a binomial sum to me, everyone. That's exactly what we would get if we did p e to the t plus q raised to which power? N. Yeah? Ah! So what does that tell you that this moment generating function came from what kind of a random variable? X distributed as what?
Binomial.
Binomial with n equal to 10. And what's p?
3/4.
Okay. Yeah. Now, let's do another one here. What if I had v distributed as Poisson with mean lambda? Okay. Do you remember what p of, right? So first of all, this thing belongs, right? This guy right here, this thing belonged to 0, 1, all the way up through n. That's what the binomial behaved as. V, if it's Poisson, I either have 0 observations or 1 observation or 2 observations, right? This belongs to 0, 1, 2, and it just goes on forever, right? Okay. And do you guys remember what the probability? So what was the probability that v was equal to x? You guys remember what the distribution for the Poisson was? What's the distribution for the Poisson?
Was it lambda e to the negative lambda x? Or am I
E to the
missing a
negative
factor there?
lambda times lambda to the x over x factorial.
sorry.
Remember that?
Mhm.
Yeah. And what about the moment generating function of v? Well, it's going to be sum x going from 0 to infinity e to the minus lambda times lambda to the x over x factorial. But then I would have to multiply by e to the tx. Yes? And what would Paul say to do with those powers that are both raised to the x power? What do you think Paul would say to do there?
Combine them and put them under the same power.
Yeah. And by the way, this thing right here, we can just pull that out, e to the minus lambda. We can just pull out. So what we're going to end up with is, let me write it this way. Lambda e to the t raised to the x over x factorial. And that thing, you have thing raised to the x over x factorial, x going from 0 to infinity. That's e to that thing. Okay, so this is going to be e to the minus lambda exponential, right? E raised to that thing that's being raised to the x power. So it's going to be lambda e to the t. And lo and behold, let me kind of go right here. This is equal to, look, this right here is exponential to the minus lambda. So can't I just straight put that inside of the other exponential also? Yeah? So this ends up being the exponential of lambda e to the t minus lambda. So let me just write lambda times parentheses e to the t minus 1. Huh! Right? So what is this guy up here? What's this distribution of y? Well, it's Poisson with parameter lambda equal to 2. Okay? So on the other, so therefore, think about it. What's the probability? The other way you could do this is you could say the probability that x plus y is equal to 2. What are the possibilities? I now know exactly the distribution of these things based on their moment generating functions, yes? I know the distributions. So what can I do? Well, for the sum of these things to be equal to 2, what are the possibilities here? What are the possibilities?
So x could be 0, y could be 2, they could both be 1, or x could be 0 and y is 2.
Exactly. So x could be 0, y could be 2, or and since we have independence, we can just do it this way, yes? Yeah. X could be 0 and y could be 2, or x could be 1 and y could be 1, or x could be 2 and y could be 0. And we know full well how to compute those probabilities. Do you know what I'm saying? I mean, they're just straight Poissons and binomials, yeah? We have those distributions, so it's just going to be sum of those three things. So in that way, we've kind of seen two different ways to compute this. We could have computed it from taking the moment generating function of x plus y, getting the probability generating function from that, taking the second derivative, plugging in 0, dividing by 2. But that seems, that might be a little bit more annoying. This one maybe seems a little bit more elegant, I guess. But those are two different ways that you could have proceeded. Does that kind of make sense?
Mm-hmm.
I mean, I'm not plugging in the numbers or anything, but you guys know what to do from here, right? You just straight plug in what those different probabilities are. What about the probability that xy is equal to 0? What about the probability that xy is equal to 0? What do you think about that? When would that happen? Now that we know everything about x and y, including like what their ranges are and everything, we figured that out directly from the moment generating function. When could the product of x and y be 0?
Isn't it just going to be 0 if x is equal to 0 and y is whatever, or they could both be 0, or y is going to equal 0 and x
That's
can be anything
right.
else?
So that means that x is 0 or y is 0. Yes? So this is the same as the probability that x is 0. Or, hey, what set theoretic operation does that correspond with? Or is,
Union.
yeah. Okay, so you have to be a little bit careful. So that means that it's going to be x is 0 plus the probability that y is 0. Is that it? I just added the probability that x is 0 and y is 0 twice. So what do I have to subtract off? The probability that they're both 0. Well, what do you know about this? Since x and y are independent, what's that going to be? Well, the product of those two. Know what I mean? Yeah? What about the expected value of xy? Come on, stop wasting our time. These are well-known, so these are independent. So what can I say that's what's going to be true about the expected value of the product? By the way, I didn't compute these things, but you know how to compute the probability that those are 0, right? Well, okay, so expected value of the product is the
product of the expected values.
Yeah, that's it. Okay, and what's the expected value of x? Being the binomial with 10 trials and proportion of success 3/4. You can do this. That's just going to be 10 times 3/4, yeah? Times, what's the expected value of y? Being a Poisson with parameter lambda equal to 2. That's just 2. Okay. There we go. Does that make sense? So, I mean, I just gave you a couple of ways you could have done the first problem where you're doing the probability of the sum of those two. But the last two parts are a little bit more straightforward now that we know what the distribution of x and y are explicitly. Does that make sense?
No.
All right. What else? Other questions? Matthew, before, did we actually go through the computation of the derivative?
Yes.
That was okay. So that was sweet. So what did we decide before? Which way did we decide was better, I guess?
Well, you said my way, where I just noticed that the distributions was kind of cheating, and so I kind of felt
Yeah.
like you were wanting us to use the probability generating function.
Oh, yeah, well, maybe, I don't know. I don't know why I felt that way that day. But certainly recognizing what the distributions are it gives a more elegant approach, yes. But if you didn't recognize the form of the moment generating function, you could have resorted to using the other one. Now, if trying to figure out what the probability of the product being 0 is, that would, that'd be a little bit trickier, but yeah. So I guess I'm fine with either of those. But it's a nice skill to be able to recognize a distribution based on its moment generating function. That's definitely a nice thing to have in your back pocket. Okay, what else? What else do you have?
So the quiz that's gonna be due on Friday, I assume that's just the normal open book
Yeah, that's right. That's right. I'm just
homework type quiz.
I'll pick something out and have you work through it. Yeah.
Okay.
So, yep. That'll just kind of keep you guys invested in the last couple little topics here. I may or may not be finished on, I'm hoping that I'll be finished on Friday, but since Monday is technically a class day, I may have 2 more lectures. But I just want to get through the central limit theorem and the strong law of large numbers. I think those are good things to end with. Chebyshev's theorem is really kind of important. And it really follows from Markov's theorem. But I've used Chebyshev a lot to prove some pretty surprising things. You use it to prove sharp concentration around means. In fact, that's exactly what we have in the weak law of large numbers, is sharp concentration around the mean. You're showing that if you let the sample size get bigger and bigger, then the sample mean random variable starts to get, more and more honed in on its mean value. Does that make sense? That's what the weak law of large numbers is saying. And that follows from Chebyshev. So basically the Chebyshev inequality shows you that even though you have a random variable, as your sample gets larger and larger, it starts to behave less and less random. It starts to actually become more predictive in nature. Starts to hunker down around its mean, so there's not as much random fluctuation as you had at the beginning. Does what I said make sense about when you look at the sample mean? Like outliers on both sides of the distribution tend to balance each other out, so you have less variability. Does that make sense? Like the variation, like if you just had an individual outcome, there would be nothing to control an outlier that's way huge in the right tail or something. But if I take a whole bunch of outcomes in the distribution and average them, then the big ones and the small ones are going to balance each other out. And so the variance drops. So it makes sense that the variance for the sample mean is like the original variance divided by n. It's smaller than it was before. And when the variance is getting smaller, that means that that the distribution is tending to hunker down around the mean. That's an amazing fact, and that's really what drives the central limit theorem forward in the end. Okay. Well, what else? Other questions? I'll post a problem, by the way, like later today. I've been writing a final for some other people. No, that doesn't apply to anyone in here though. Okay. So I'll put that out later today. But anything else? Well, I appreciate you all. Thank you for your faithfulness and coming and asking good questions. That's helpful for everybody, I think. All right. So, hey, I'll let you get back to whatever you guys were doing before you came in here.
Thank you, Dr. Hammett.
Yep. Have a good rest of the day.